Welcome, Zach Clarke. Thank you so much for meeting with us today. We are excited to hear a little bit about what it is that a systems engineer does. So would you start off today by sharing a little bit about who you are and kind of how you came to be involved in space?
Yeah, so as mentioned, my name is Zachary Clarke. Um, I'm an engineering student. I grew up loving space. I I fell in love with, the old Star Trek and Star Wars movies. And when I was a very young child, I would always grab the big encyclopedias with the big pictures of Jupiter and asteroids, and I'd read them all the way through and learn as much as I could about the environment. Eventually, I made my way to Utah State University for its engineering degree. And when I got there, I learned that Utah State sometimes refers to itself as Utah Space University. And I got involved with the Getaway Special Club at Utah State, where undergrads put together CUBE satellites. They recently just launched their mission in 2021, where they tested a new inflatable boom, which was really exciting. While I was there, I got connected with professors like Charles Swenson, who invited me to come take his space systems engineering class. And that's where I learned what systems engineering was and how it took a whole bunch of concepts that engineers do and bring them all into one package, which is something I was very interested in. As much as I appreciate depth knowledge and um, the level of expertise that engineers who study one particular focus can bring to a team, I saw myself as more of a breadth type engineer who wanted to have his finger in every single pie and wanted to be involved in the greater conversation. So I studied under Dr. Swenson there. He invited me back for a master's degree in space systems engineering. And here I am today, just working under him and managing undergraduate teams and preparing for a future in space systems engineering.
That's fantastic. Now, did you grow up in Utah or did you go across states to attend there? What's your
I did. I grew up in Utah. I'm from a town called Enoch. It's next to Cedar City, Utah, down south. Population blink and you'll miss it.
I see.
Yeah, but
So
I had some good opportunities down there. I attended Southern Utah University to get my associate's degree while I was still in high school. And I went through a program called the Success Academy program, which hooked me up with some STEM opportunities. I worked with robotic cars and the Science Olympiad competitions.
that's great. I think sometimes our students think that they can only go to a four-year school, like that has to be their path. But we have actually podcast with a few students that are remarkably successful, but they started in a two-year degree program, right? And they really, I think maybe that helps kids mature maybe and figure out what they want to do.
Right. I'm thinking it helps you to kind of hone that area of interest, or you
Right.
can at least dabble in something broader before you specify.
Right.
Oh, yeah.
So we just, for our listeners, I just met Zach at SmallSat. Zach, how many years? Tell us about your experience with SmallSat, or if this is your first one, what were you there to accomplish?
That was my very first small sat. Um, I was there to share a new teaching technique that we developed for our undergraduates called parallel flight system development. The idea behind it is you have a professional company and a class of undergraduate students begin developing a space flight system at the same time. In this case, we secured a $5 million contract from NASA to develop high altitude cryogenic instrument sensors, specifically a satellite mission for the instrument High Tide, which is designed for large bus-like satellites that are really large and really expensive to put up there. And Utah State had been working on a technology called ATA, which would allow us to cool cryogenic instruments to the correct temperatures so they can function properly, which is unprecedented in the CubeSat community. So we developed the mission side by side with a professional company called, wow, brain fart, Orion Space Solutions.
Okay.
And we would develop our system, and then they would come and work with us and edit and critique our system and help us reach the next level. And in return, we would provide inspiration and work and analysis that they desperately needed on their side. And together, by the end of the semester, we had a complete system, well, two different systems, a student system and a professional system, that then Orion Space Solutions could choose which one to go with. They ended up going with the student solution because it was more adaptable and flexible to the changing requirements at the time. And we are scheduled to launch sometime in 2024, which is really exciting for our undergrads. It's really exciting for me, for Dr. Swenson, and for all of us at Utah State and Orion Space Solutions. So
For
we
some of
wanted to
our
share that
younger,
with people.
sorry
We
about
wanted
that. I
to
didn't
share
mean to
that
cut you off.
experience.
But yeah, that, so first of all, I'm trying to like remember I'm not as techie, right? And so even some of our listeners might be wondering, when you said that obviously there's a correlation for the cooling and the CubeSats, why is it important for our younger listeners to make sure that that cooling takes place, with particular in relation to CubeSats?
There's a lot of science behind it, right? In this case, certain sensors require really, really low temperatures in order to function properly. In this case, the high tide instrument uses super cool temperatures to help discern different types of gases in the atmosphere. That was the instrument we were flying on ACMES. It's really important because thermal systems usually require a lot of surface area in order to capture that heat and dissipate it out into space. And thermal systems that are capable of getting instruments to those really low temperatures are so large and cumbersome, they normally don't fit on cube satellite models. The ATA, which Utah State's been developing for the last 4 years, I want to say 4 or 5 years, don't quote me. It is a 1U instrument, which means it only takes up a 10 centimeter cube space, which is really small. It functions really well. And this mission will move it from technology readiness level 5, which means that we've done all the ground testing and it doesn't leak anymore. And we're confident that it will function. It'll take it to technology readiness level 6, which is where we can start putting it on other missions under the expectation that it will continue to work. And that's a pretty monumental deal, especially for the students who've been developing it. Fun fact, it's again, it's another student-driven project. Everything that we do at Utah State, for the most part, there's a few exceptions, but everything we do, it's done by the students. They're the ones who are in the lab putting it together. And then a lot of the times they'll take these products that they make and they'll go and take them to either the companies that end up hiring them, or they'll create new companies from that technology. And it's just kind of fun to see how the circle of life, if you will, or the circle of engineering or education kind of propagates out from there, which is real fun to see.
So we need to unpack about 5 things in what you just said. So let's let's unpack it for our listeners. First, Utah State does very hands-on engineering, very real world, very authentic, very useful projects. Number 2, you've mentioned Dr. Swenson twice. My students actually met him at Coast Bar in Athens this summer. And I did not meet him. I was not with the group of kids that met him, but they said he was very approachable and he was just a genuinely nice guy. So that's something I wanted to share with you. Also, I wanted to share for our listeners that may not understand anything about thermal management of a satellite. If I sit here and I'm hot, I can turn on a fan and the fan will blow air across me, and through conduction, my body can transfer heat to air molecules, right? But in space, with our spacecraft, we have no medium to physically move the heat to, so all we have is radiation, right? That's really what we have to radiate heat off of our spacecraft. So what you said is so unique about what you guys are doing is the temperatures you can achieve in such a small surface area or in such a small apparatus, or the sensors that you work with. Is that a fair summary?
Very.
Well, it sounds like not only the actual project is unique, but I'm wondering about the process as well, right? So obviously with something that that is this big, it's going to be over the course of time. And I know you mentioned it was something that you've done for a couple of years now. Can you talk to us a little bit about how important that process of like coming up with an idea, how you end up fleshing it out, how, the whole iteration of that, the reiteration, and how you get to from point A to point
And the creativity. Yeah, we're curious about the learning, and as she said.
Well,
yes.
right, and I'll just give you the brief background on that. And you probably met some of our kids. Some of our kids, they've learned that there's nothing really in science that's going to happen overnight. So if you're looking for short term, I've already succeeded, I got the answer right away. That's not going to happen. A lot of our kids, at least with even a CubeSat, it's a 3-year minimum kind of commitment. So tell us a little bit about the process that they're doing, that they're allowing these kind of big projects to happen
With your companies. Yeah.
Okay. Where to start? That's a kind of a big one to
Big,
tackle.
right?
Well, you started with me with pre-phase A's. When I met you, you mentioned pre-phase A. Maybe you could share a little bit about the engineering design process that you lived through, right? And
Right.
for our listeners, TRL, he dropped TRL on you. That's something I forgot to define for the audience. Technology readiness level. So you imagine 0 to 9. And of course, Zach, correct me if I'm wrong. 0 is you and I sit in a bar and we draw something on a napkin and we go, hey, this would be cool.
That's
and
about
then
right.
TRL 9 means it is a proven technology with heritage in space. It successfully flies in space, and it becomes sort of one of our off-the-shelf type systems that we can rely on. Is that fair?
That's very fair.
Okay. Now, how does this process work? The program that you enjoyed so much.
Well, it starts very much how you described. You sit at a bar with a napkin and you think, well, this will be cool. In this case, NASA approached us really about wanting to fly their instrument, the high tide instrument. And we put out a bunch of proposals and showed that we could do it, and that we had some really good ideas and concepts. And then we won the contract. That's great. That's awesome. And then we all look at each other and go, cool, now what?
Yes.
Yeah.
We do that. We do that on a much smaller level.
No, it's good fun. One thing that I really appreciate about how Dr. Swenson teaches the class is on the very first day he walks into the class, introduces himself, and looks at everyone and says, okay, I have no idea what I'm doing. So let's start brainstorming and get to work. And what ends up happening is we're presented the mission problem. And this is the same with the professional company, Orion. They were given the mission problem also. And then you just kind of squirrel yourself away for a couple of ideas and you start drawing pictures. You start thinking to yourself, okay, how do I want to try and solve this problem? How do I want to do this? And you come back together with your group, with your team, and you present these pictures. They're called CONOPS, or concepts of operation. And they're supposed to be bite-sized morsels that someone can look at, and in about 30 to 45 seconds, have a pretty good idea what you're thinking, what you want to do. It's not supposed to have a lot of analysis to it. It's just a quick picture, a quick idea. And you can have a CONOPS for many, many different topics. And I remember we all got together on that first day, and there were about 35 completely different pictures about completely different aspects about the entire mission. And we all looked at each other and were like, well, we're not on the same page at all. But that's where you start. You have to get all the ideas out there. You have to get people talking, and you get a dialogue going. And ultimately, the first 2.5 months of this process is just getting people on the same page and understanding that we have a unified idea for this mission. And once we all agree on what we want to do, then we can actually start the analysis. And a lot of our students fell into a trap where they started doing the analysis and they would spend hours and hours figuring out all of these numbers and procedures. And then we'd throw the idea out the window because there were other things we wanted to try. And that can be very frustrating sometimes. And we appreciate their hard work, and they gave very convincing arguments for what they wanted to do. But that's also why we try and keep things very light in the beginning, is so you don't put lots of effort running your wheels when you really have no idea what you're doing yet.
So it sounds like you are taking everyone's concepts, right? And then from those, you're deciding and narrowing it down to, well, we might use this from this person's, we might use this from this person, and coming up with then a combined idea, so that getting too far ahead of yourself to like prove why this was going to work was not as relevant as just the actual thought process, because you didn't know where it was going to come from. Is that right?
Exactly. And more than that, as you do this, you start thinking it through, and a problem you didn't think about 2 days ago all of a sudden pops up, and then another problem pops up. And PowerPoints are a lot cheaper than mechanical devices.
Oh, yeah.
Yeah.
Hey, quick question. Were you given a very simple mission statement, or were you given a very precise list of requirements? Because it sounds like you may have had to create some requirements as you went along the way. How did that work?
Well, that's the next step, really. We started with a very simple mission statement to start developing these concepts of operation. And then as soon as you decide on one really good idea, you start to draft up the requirements. And those are really important because the requirements define the mission. Once you have your requirements written down and set, that is what you engineer to, that is what you design to. And they're used to put a box around what the mission is going to be. So in our case, one of our requirements is that our cube satellite needed to maintain temperatures of 0 degrees Celsius for 45 minutes at a time. And where did that requirement come from? It came from the high tide instrument, which we wanted to collect data for 45 minutes at a time. So at a minimum, we had to keep it at a really low temperature for that amount of time. Now, why do we make it a requirement? A requirement is important because it acts as a contract between two subsystems, so that both of them agree that they will work together to reach that requirement. Without requirements, or more specifically, without good requirements, because you can have some very bad requirements, as we found out. With good requirements, I just lost my train of thought. That's okay. Good requirements are really useful. They keep everything in line. They keep everyone organized, and by adhering to the requirements, you facilitate development much faster, much more streamlined, and everything just works a lot better.
Would you say that if you hit all of your mission requirements, then you have mission success? Is that a fair statement?
Yeah.
I have a question about, you had said that NASA kind of came up with this need or whatever their problem was or whatever, and they selected you all and is to do the contract, I guess. So how often does NASA send out these kind of proposals or requests, and how do they narrow down? How do they make their selection to even send it out to, like, are there a lot of schools, or is it down selection? How does that go?
As far as I understand, NASA routinely puts out feelers into the community, where they will say, hey, we have this pot of money and we have this idea that we want solved. Who's interested? And then teams will write up proposals about how they would solve specific missions. In this case, we were a research contract where NASA just said, hey, we want to put some CubeSats on one of our missions coming up. What ideas do you guys have? And as I recall, I think 30 or so universities applied, and we were number 7 on their list of missions that they found interesting. And then after we put out the proposal, we went through a whole nother round of interviews, if you will,
Right. Like
where they
decide and select.
confirmed that they wanted to do our mission.
I love that idea of how, you have NASA who's going to say, hey, it's almost like, it's obviously the real world connection that you were talking about before, right? And so it gives everyone that chance to walk through that process. So now I'm imagining what you'd have started with we all come up with these ideas, we get together, we create one model for that. And that's ultimately what goes to NASA for the proposal. Is that correct?
Yes.
So I was totally captivated by your description of this process you went through in college, where you worked in parallel with a real company on a real world project. Yeah. I'm actually going to try to implement it with my middle and our middle and high school students down here. let's move to the present. And what would you like to share with us about where you are now and what you hope to do? Maybe you could describe what is the ideal job for you as a systems engineer. If you could draw up your own, if you could create your own job description, what might that be?
So an ideal job, something I would strive and aim for. If this landed in my lap, I'd pick up everything and go. I would love to be a systems engineer for a company that builds CubeSats, just like what I did in college. My ideal career is I would be in charge of teams. So there'd be some large mass of engineers all working on their little projects and working to fulfill the requirements. So they would all answer to a subsystem head who would be in charge of thermal systems, of power systems, of the mechanical system. And all of these systems head would come up to me and us and my small team that I would have, because there's no way I'd be able to do this all on my own. And my job would be to manage and facilitate the development of the project, to make sure that everyone was in line with the requirements, to interface with the customer, to make sure that their needs were being met. And then taking customer requirements, which are oftentimes very non-technical, which is a good thing. I love working with non-technical people because I think that they're more interesting. No offense, engineers. The art degrees are valuable, but they do not understand a lot of the times the technical language needed to describe these systems. And so in my ideal career, I would talk to these people and translate their thoughts and their feelings and their emotions into engineering requirements that I can then hand to the engineers and say, okay, build this.
Right.
No, CubeSat is art.
Yes.
That's what that sounds like.
So
I love it.
your dream job is to be a liaison, a coordinator. You want to be Gene Kranz in the CubeSat world, right? You want to, I can make sure that your interview goes to Terran Orbital. Their global headquarters is in our county here in Florida. And they're building a massive CubeSat factory up at the Space Coast. But I'll make sure, since we're into some discussions with them on some projects, that they get your podcast.
Well, I would appreciate that.
Oh man. And we have OneWeb. We actually toured the OneWeb factory in Space Coast. So they build microsats on the frequency of about 1 a day.
Well, I was thinking more like near space launch.
Yeah.
Is that what they're kind of working to do too?
Oh yeah. And near space launch, our friends in Indiana, they when I met them 6 years ago, they had 16 subsystems on orbit. Today they have 800, and they just launched their 100th CubeSat. And they were like, I don't want to say a mom and pop shop, but they were 2 professors at a Taylor University that were early adopters, and along there with Twigs. But Zach, this is fantastic. If you were in Florida close to us, I would literally try to either beg, cajole, or hire you to mentor our kids in a live setting.
Well, we could even do it online. So he'll get you to talk to the Wolfpack at some point. I'm sure of that.
I would love to do that.
I would love to do that. I watched your little your introduction video, where all the students were lined up and they were all professionally dressed. And
oh yeah, on the Wolfpack site.
Oh yeah, I thought that was absolutely splendid. And it was real funny because as I was watching them, I was like, that's me. That's what I looked like when I was that age.
Yeah, right.
Yes.
I was totally that kid.
I want to thank you for doing a shout out for our web pages too. That's
wow,
really
we got
great.
an extra visitor.
So little funny thing, I used Star Trek music on the one that YouTube let me use, but I also put that video to ACDC and they would not let me. I had a copyright infringement or something on ACDC music. But Zach, this has been fantastic. I really have enjoyed this.
Before we get to our concluding question, which is always super easy, I just want to make sure that I, as the non-techie, right, I'm more of an artsy kind of person, make sure that I understand systems engineering now from having been here to. So it sounded like you had opened up by saying that a systems engineer is someone who takes bits and pieces and puts them together for this larger puzzle. And that's exactly what you did with this project, which allowed you to not only create those puzzle pieces yourself, but to have other people contribute these pieces of the puzzle that created this larger whole. So when you then described your ideal job, it sounds like a systems engineer it doesn't have to be tied to one thing. It sounds like anyone who's taking the different subsystems of whatever it is that you're working on is just helping to integrate to make that a larger whole. And I also really loved how you talked about translating, because I think that that would be a great kind of job description for, it sounds like what you would be doing as a systems engineer, and that's translating the visions to create that picture out of the puzzle pieces. I don't know. Am I right? Did I walk away with a clear idea?
Yeah, that's very
Yay.
much what a systems engineer is. 10 out of 10. I
sounds
think the only
beautiful.
thing I would add is a systems engineer needs to have a lot of knowledge about a lot of different
All of the
things,
systems, yeah.
but they aren't necessarily the expert either. And that's what I love, is because I feel very intimidated, and sometimes I don't think I have enough knowledge to really make big decisions. But that's okay, because there's 6 other experts and I can go ask them and they can figure it out. And I just have to make sure that they're talking to each other and that I understand enough that I can push them together and help everything come to a complete product.
It's
Yes,
communication.
you have really emphasized, without saying it, the importance of soft skills
Mhm.
in the life of a systems engineer, about the way you relate to your other subsystem
And having to
leads.
see a larger picture. I think
Yeah.
that's very
Yeah.
creative, right? You have to be
Pull
creative
the
to see
pieces
the
together,
pieces.
pull all the pieces together.
Yeah.
So,
All right. Well, the last question is super easy. So we've got people who are listening who might want to do what you're doing, who are inspired today to be like, yes, now I know that there's this job for me. What advice do you have for those listeners as they're about to maybe head to high school or college and beyond, if they want to pursue this path?
All right. So my first thing of advice, something that I wish I could have told my younger self, is engineering is very, very important, but it's also important to feed yourself and to go to sleep on time and to get exercise and to run around and be a normal person. I have watched too many friends, and myself included, who just hit the wall really hard when they want to go hard to the paint and they want to do a great job, and they end up burning themselves out. So work-life balance, take care of yourselves, please, because you're going to get to the career one day. We need you in tip-top shape, both mentally, but also physically. My second piece of advice is be prepared to fail and learn to embrace failure, because in doing so, you will learn so much more, and be humble. That's another thing too. In doing those things, you will learn so much more, and you will draw connections to people that you otherwise wouldn't. Very, very important. And then finally, just don't give up. Some of you will do awesome and just sprint right to the end, and others will. A little bit about me. It took me 6 years to get my undergraduate. As a high school student, top of the line, straight A's all the way across. And then I got to college and life changed.
Yeah.
Six and a half.
That's okay.
Six
So
and a
just-
half.
Oh, there you go. And
Six and
you
a
know,
half.
I think that that extra time really helped me as a person. I matured. I learned things about myself. I learned things about engineering, ironically, that I don't think I would have if I had just gone through in 4 years. And there's a lot more opportunities now that I have as an older student who took the time and really let things settle and develop and failed, that I appreciate and I wouldn't change for the world. So those would be my piece of advice. Take care of yourself, be prepared for failure, and don't give up.
Excellent.
Fantastic.
Really, really good
Fantastic.
stuff. Thank you so much for, not only sharing that advice, but for spending some time with us today to kind of describe what it is that you do. I know Kevin was really excited after meeting you, that you were here. So I know that our kids will look forward to meeting you at the Wolf Pack. So I'm sure Kevin will set that up.
Oh yeah, I would love to participate that any way I can. So.
Got it.
Well, thanks so much. And don't discount the idea that we might circle back with you in a year or so and follow up with you and have a subsequent interview, because there's always good projects out there, and we appreciate your time. You were great. Thank you.
Perfect. Thank you.